A second here lasts a century somewhere else. We are traveling to the quiet galaxies where time flows differently from our own. A cosmic secret hidden not in violent black holes, but in the deep silence between the stars. By the end of this journey, you will see the universe not as a single stage, but as a tapestry of countless timelines. What does a slower ticking clock mean for the life and death of a star? How does the void itself shape the passage of eons? What would it feel like to stand in a place where time itself has fallen asleep? Our everyday experience tells us a second is a second, anywhere you go. But the universe operates on a far more complex set of rules. Time itself is not a constant river flowing at the same speed for everyone. It is a variable, a flexible fabric that can stretch and compress, its flow dictated by the twin forces of gravity and motion. This is the profound revelation from Einstein's theory of relativity. Picture a strong gravitational field, like the immense pull of a black hole. There, time is stretched thin, slowing to a crawl relative to a distant observer. But now, let us turn our gaze to the opposite extreme, to the immense voids between the great clusters of galaxies. These are the emptiest places we know, where matter is so sparse that gravity's grip is almost non-existent. In these cosmic deserts, far from any major source of mass, time is actually free to tick faster. It flows more swiftly than it does here in our Milky Way, a galaxy of average density. This means the universe has no single master clock. There is no central timepiece dictating the rhythm of existence for all. Instead, the expansion of the universe itself creates isolated pockets, entire regions where the local density of matter and energy directly writes the rules for time. The more stuffed with matter a region is, the more time is slowed by gravity's relentless pull. The emptier it is, the faster time can run. This cosmic variability is the fundamental key, the first step to unlocking the secret of those quiet galaxies where a single moment for us could span an entire geological age. This relentless expansion is the engine behind the entire phenomenon. We often picture the universe growing like a rising loaf of raisin bread, with the galaxies as the raisins moving apart as the dough expands. But the dough itself is space-time, the very fabric of reality. Now think about that fabric in two different places. In a dense galaxy cluster, gravity acts like a powerful anchor, pulling space-time taut and resisting the expansion. The fabric is held tightly, and time, woven into that fabric, is slowed down. But travel out into the vast, empty cosmic voids, the emptiest places in existence. Here, there is almost no gravity to fight the expansion. Space-time is free to stretch, and as it stretches, time itself is pulled along, ticking faster. This is where the Hubble constant, the measure of the universe's expansion rate, becomes deeply personal. It is not just a number for the whole cosmos. Its local influence is shaped by what is, or more importantly, what is not in the neighborhood. Cosmologists point to the vacuum energy of empty space, a faint background energy that permeates the void. In these near-empty regions, this energy can dominate, gently pushing the expansion along and allowing time to flow at its most rapid, unencumbered pace. So the very emptiness of a void is what creates a river of time that runs swift and deep. This sets our course. To find where time flows differently, we must hunt for the most isolated galaxies, islands adrift in these seas of nothingness, where the local clock is set by the void itself. These quiet galaxies are the cosmic equivalent of hermitages, isolated retreats deep in the wilderness of space. They are often ancient elliptical galaxies, vast spheres of old, red stars, or faint dwarf galaxies, the faintest smudges of light. Their home is the cosmic boondocks, the emptiest stretches between the great supercluster filaments. What makes them truly quiet is their low metabolic rate. Unlike vibrant spiral galaxies like our own Milky Way, constantly giving birth to new stars in bright, gaseous nurseries, these galaxies have settled into a deep stillness. There are no violent galactic mergers ripping through them, no bursts of frantic star formation. Their gravitational and energy fields are calm and stable, almost serene. This profound tranquility is what makes them so special. Without the constant cosmic noise of stellar explosions and colliding gas clouds, the subtle, background effects of the universe itself can be heard. The gentle stretching of space-time, driven by the expansion of the universe, is no longer masked. In these quiet places, the effect of this expansion on the local flow of time becomes something we can actually measure. Astronomers hunt for these galaxies in vast catalogs like the Sloan Digital Sky Survey, which has mapped millions of celestial objects. They search for the specific signatures of quietness, extreme isolation, and a lack of the blue light that signifies young stars. These galaxies become our perfect laboratories. They are the still ponds where we can see the ripples of time itself, undisturbed by the splashes of a more chaotic cosmos. But black holes are not the only masters of time. Every galaxy, even a quiet one, is a massive collection of matter, and all that mass warps the fabric of space-time. This is gravitational time dilation operating on a truly cosmic scale. Picture a clock placed high on a mountain. It will tick ever so slightly faster than an identical clock at sea level. Why? Because the clock at sea level is deeper within Earth's gravitational well, and gravity slows time. Now magnify that idea to an almost unimaginable degree. A galaxy with its billions of stars, its swirling gas, and its immense invisible halo of dark matter creates a gravitational well far deeper than any planet's. Every single object within that galaxy, every star and every potential planet, is essentially a clock sitting at the bottom of that well. Their time flows more slowly compared to the almost perfectly flat spacetime of the empty cosmic void outside. This is not a small effect we can ignore. We can describe it using the same physics that describes the space around a black hole, a framework known as the Schwarzschild metric. While a galaxy is not a black hole and its gravity is far weaker, the principle is the same. The combined gravitational pull of all the galaxy's components, especially the dominant dark matter, creates a measurable slowing of time. The mathematics shows us that the difference in time flow between the heart of a galaxy and the emptiness outside, while tiny in any single second, accumulates over millions and billions of years. This means a quiet galaxy is not just a place set apart by its location. It is a place with its own distinct temporal reality, a pocket of the universe where the local clock is set by two competing forces. The expansion of the universe, dominant in the void, tries to speed time up. The galaxy's own gravity, holding everything together, works to slow time down. The result is a unique time zone, a specific rhythm of existence that is entirely its own. This leads to a profound question. If these galaxies are pockets of altered time, what would it be like to witness the universe from within one? Our own galaxy sits within a bustling neighborhood, a cosmic cityscape where gravity's influence is strong and time is slowed. From this vantage point, we peer across the unimaginable gulf of space at those distant, quiet galaxies. Yet this act of observation is not a simple look through a window. It is a view into the deep past, and it is a view from a region of slower time looking into a region where time, theoretically, flows faster. This creates a profound puzzle for any astronomer trying to measure these subtle effects. We are essentially trying to measure a slow clock from inside a room where our own clocks are running even slower. The primary tool we use to gauge the expansion of the universe is redshift. As light travels across the expanding cosmos, its wavelengths are stretched, shifting it toward the red end of the spectrum. This cosmological redshift tells us how much the universe has stretched during the light's journey, but layered on top of that is another, more subtle effect. If time truly flows faster in the void around a quiet galaxy, then the very rate at which light waves are emitted from its stars is different. An atom vibrating in that distant galaxy might emit light at a certain frequency from its perspective, but from our slowed-down perspective in the dense local group, that frequency could appear shifted. We have to ask, is the light we see reddened only by the expansion of space, or is part of that shift due to the fundamental difference in how time was flowing at the source? Disentangling these two effects is one of the most delicate challenges in modern cosmology. It forces us to acknowledge that we are not passive viewers of the cosmos. We are active participants within it, and our own local reality, the very speed of our own time, colors everything we see. To solve this, astronomers turn to the most stable cosmic light sources they can find, like Type Ia supernova. These stellar explosions have a known intrinsic brightness, acting as standard candles across the universe. By carefully analyzing the light from these events in both dense galactic environments and in the quiet, isolated galaxies, scientists can look for tiny discrepancies. They search for a signature in the light that cannot be explained by expansion alone, a faint whisper that speaks of a different tempo of time at the source. This is the painstaking work of listening for a single, quiet note within a cosmic symphony, a note that tells us that the universe is not just expanding, but that it ticks to the rhythm of countless different clocks. A spectrograph is the ultimate cosmic translator, turning silent starlight into a story of time. When a massive telescope like Hubble or the James Webb Space Telescope collects the faint glow from a quiet galaxy, that light is not analyzed as a single white beam. It is funneled into a spectrograph, a brilliant instrument that acts like a super-powered prism, splitting the light into its constituent colors to create a rainbow spectrum. But this rainbow is not smooth and perfect. It is marked by dark and bright lines, the unique fingerprints of the elements that created the light. One of the most crucial of these is the hydrogen alpha line, a specific signature produced when an electron within a hydrogen atom drops to a lower energy level. Back on Earth in our laboratories, we know the exact frequency of this event. It is a known quantity, a reliable atomic clock that ticks at a precise, predictable rate. When we observe the hydrogen alpha line in the light from a quiet galaxy, we are reading that distant atomic clock. If the line appears shifted toward the red end of the spectrum, it tells us something profound has happened. Part of that shift is the familiar cosmological redshift, the stretching of the light wave's journey across an expanding universe. Yet another component is far more intimate. It is a direct record of the tempo of time in that galaxy's home. If time were flowing faster there, the very oscillations of the hydrogen atom would have been faster from its own perspective. The light waves emitted would have been subtly different from the moment they began their journey. Our spectrographs capture this by comparing the observed frequency of the hydrogen alpha line to its known rest frequency, and then carefully subtracting the calculated effect of cosmic expansion. Astronomers are left with a tiny residual signal. This leftover shift is the whisper of a different clock, the first direct evidence that the atomic processes in a distant island universe do not tick in perfect unison with our own. This is how raw data, columns of numbers from a telescope sensor, are transformed into a measurement of time itself. It is a meticulous process of listening for a single, pure note amidst the cosmic noise, a note that confirms our universe is woven from countless threads of time, each moving to its own distinct rhythm. Deep in an immense cosmic void, far from the bright ribbons of galactic superclusters, astronomers found a perfect laboratory. It was an ancient elliptical galaxy, a silent, red sphere of aging stars that had drifted alone for billions of years. When they measured its light with extreme precision, a puzzle emerged. The galaxy's redshift, the telltale sign of cosmic expansion, was slightly off. After meticulously accounting for every known factor, the galaxy's motion, the universe's overall expansion, and instrumental errors, a tiny but persistent anomaly remained. The light arriving at our telescopes carried a signature that could not be explained by motion or distance alone. The most compelling explanation was that time itself, in the heart of that quiet galaxy, was flowing more slowly than our models predicted. The combined gravity of its stars and its immense halo of dark matter had created a pocket of decelerated time, leaving its faint mark on the light that finally reached us. The lead researchers on the project described their initial reaction as profound skepticism. "We spent months trying to kill this signal," one astronomer recalled. "We checked our instruments, our software, our models for interstellar dust. The anomaly refused to go away. The path to acceptance was a long and rigorous peer review process, forcing other teams to replicate the analysis and challenge the methodology." It was only after independent confirmation that the scientific community began to seriously consider that they were not just looking at a distant object, but peering into a region of spacetime with a fundamentally different rhythm. This was not just a theoretical idea anymore. It was a measurable fact etched into the spectrum of starlight. If such an effect can be detected in one galaxy, what other temporal wonders are waiting in the even quieter, more isolated corners of the cosmos? That persistent, unexplained redshift anomaly in the isolated galaxy points toward a force even more fundamental than gravity: dark energy. The mysterious repulsive force driving the universe's expansion to accelerate is the silent architect of these temporal landscapes. While gravity pulls matter together and slows time, dark energy does the opposite. In the profound emptiness of cosmic voids, where matter density is nearly zero, dark energy dominates completely. Its repulsive effect works to stretch the very fabric of spacetime, and as that fabric thins and expands, time itself is pulled along, flowing at its most rapid, unencumbered pace. Think of spacetime as a vast, elastic sheet. Gravity, from galaxies and dark matter, creates heavy dimples in that sheet, places where the rubber is stretched tight and time moves slowly. Dark energy, however, is like a constant, gentle pressure from below, inflating the entire sheet. In the empty regions between the dimples, where there is no gravity to resist, the sheet stretches the most and time rushes forward. This brings us to the great theoretical debate. What exactly is dark energy? The leading idea is the cosmological constant, a concept originally proposed by Einstein. It suggests that dark energy is an inherent property of the vacuum of space itself, a constant energy density that never changes. If this is true, then the rate at which time flows in the emptiest voids is also a constant, a fixed feature of our universe. But another compelling theory, called quintessence, proposes that dark energy is a dynamic field that can change over time and even vary across space. A quintessence field could mean that the flow of time is not just different from place to place, but that it could be evolving, perhaps accelerating in its own right as the universe ages. This discussion moves from abstract equations to observable reality when we look at our quiet galaxies. These isolated island universes are the precise locations where the tug of war between dark energy and matter is most evident. Their light carries the imprint of this cosmic struggle. By meticulously measuring the redshifts of these galaxies and comparing them to their counterparts in denser regions, astronomers are not just measuring distance. They are taking the temperature of dark energy itself, testing whether it is a simple constant or a dynamic, changing force. The rate of time in the deepest void becomes a direct probe into the deepest mystery of our cosmos, connecting the largest scale force in the universe to our most fundamental experience of a moment passing. The light from the Big Bang itself carries a whisper from these quiet galaxies. This third and most subtle clue is known as the integrated Sachs-Wolf effect, and it connects the oldest light in the universe to the slow ticking of time in distant islands. To understand it, picture the cosmic microwave background as a uniform sea of radiation, the faded afterglow of creation. As these ancient photons travel for billions of years to reach our telescopes, their journey is not through empty space. They pass through the gravitational landscapes sculpted by galaxies and the voids between them. A gravitational potential is simply the slope of spacetime's terrain, a hill or a valley created by mass. When a photon flies into a gravitational valley, like the region around a massive galaxy, it must climb out. To do so, it expends energy, and this loss of energy is measured as a slight reddening of its light. Conversely, if a photon travels through a region where the gravitational landscape is flattening out because the universe is expanding, it can actually gain a tiny bit of energy, shifting slightly toward the blue. Think of a sound wave traveling through a dispersing crowd. As the crowd thins, the wave loses less energy to the surrounding bodies, and its character changes. Now apply this to a quiet galaxy where time is slowed. The gravitational well there is deep and stable, but it is also ancient and no longer growing dramatically. As the universe expands, the well's relative influence on the fabric of spacetime evolves. When a cosmic microwave background photon passes through this evolving gravitational territory around a quiet galaxy, it experiences a specific, subtle shift. The photon's energy is imprinted with the signature of that galaxy's unique temporal rhythm, a faint fingerprint of its slowed down time. This is not a direct measurement of the galaxy's light, but a measurement of how the galaxy's gravitational presence has altered the oldest light in the universe. Data from the Planck satellite mission, which created exquisitely detailed maps of the cosmic microwave background, has revealed these very correlations. The subtle temperature variations in the Planck map, those tiny cold and hot spots, align statistically with the locations of supervoids and the isolated galaxies within them. It is a second, independent witness to the phenomenon. While the redshift of a galaxy's own starlight tells us about its local clock, the integrated Sachs-Wolf effect tells us how that galaxy's time-warping gravity has echoed across the cosmos, leaving its mark on the primordial radiation. Two completely different lines of evidence, one from the recent light of stars and one from the ancient light of creation, are now pointing to the same incredible conclusion. These are not just quiet places, they are places where the universe itself is breathing at a different rate. A slower clock rewrites the entire life story of a galaxy. Within a quiet, isolated galaxy where time is stretched thin by gravity, every cosmic process unfolds with a profound lethargy. The frantic bursts of star formation common in denser galactic neighborhoods are replaced by a deep, prolonged stillness. The rate at which giant molecular clouds collapse to ignite new stars, a process that might take only a few million years in a busy spiral galaxy, could be drawn out across many times that duration. This stretched timeline means the galaxy's stellar population ages at a different rhythm. The brilliant, short-lived blue giants that light up spiral arms are even rarer, their explosive supernova deaths occurring less frequently. primary evidence for this lies in the color and chemistry of the starlight itself. Astronomers compare two galaxies of similar mass, one in a dense cluster and one adrift in a void. In the cluster galaxy, the main sequence turn-off point, the specific brightness and color where stars are just beginning to exhaust their hydrogen fuel and leave the main sequence, appears much brighter. This indicates a younger, more recently formed population of stars. In the quiet void galaxy, that turn-off point is significantly dimmer and redder, signaling an older stellar population where star formation effectively wound down eons ago. The chemical fingerprint tells the same story. Elements heavier than hydrogen and helium, which astronomers call metals, are forged in stellar furnaces and scattered by supernova. This process of galactic chemical enrichment happens in slow motion within a quiet galaxy. Its stars show lower overall metallicity, a testament to a more gradual, drawn-out history of stellar birth and death. The very metal content of a star in such a place is a direct record of the slower tempo of time in its home. This reveals that time dilation is not a background effect, but an active participant in shaping a galaxy's destiny. It dictates the pace of its growth, the aging of its stars, and the ultimate richness of its chemical elements. If life were to arise on a world orbiting one of these ancient, metal-poor stars, how would its perception of the cosmos differ? Would its astronomers, looking out from a pocket of slowed time, see a universe that seems to be rushing headlong toward its end? A civilization born within a slow-time galaxy would perceive a universe in fast-forward. From their perspective, nestled deep within a massive gravitational well where every second is stretched, the cosmos outside would appear to be a place of frantic, almost incomprehensible haste. Stars in other galaxies would flare into existence and explode in what seemed like a brief, brilliant flash. Entire galactic empires of life, should they exist, might rise and fall within the span of a single one of their generations. Their entire astronomical history would be one of watching the universe age and evolve at an accelerated rate, a silent movie playing out at double speed just beyond their window. This warped perspective forces us to confront a difficult question about our own existence. The anthropic principle suggests that we observe a universe compatible with our existence as conscious observers. We find ourselves in a region of space-time where the flow of time is neither too fast nor too slow to allow for the gradual, billion-year processes of planetary formation, chemical evolution, and the slow, painstaking development of complex life. If our local time flowed significantly slower, the window for life to emerge might close before the first single-celled organism could even form, as the raw materials for planets themselves would take too long to coalesce. Conversely, if we were in a void where time raced, the universe might rush from its birth to its heat death in what felt like a cosmic instant, leaving no stable epoch for intelligence to arise. Our very presence here in this galaxy at this time might be a direct consequence of living in a Goldilocks zone for time itself. For a hypothetical intelligence in a slow-time galaxy, their technology and science would develop along a fundamentally different trajectory. A long-range space mission that takes 10,000 years for us might represent a commitment of only a few centuries for them, a manageable time frame for a patient, long-lived culture. But their greatest challenge would be information. The data they receive from the outside universe would be a compressed, high-speed record of events that were already ancient history. To understand the cosmos, they would have to become masters of deciphering this accelerated timeline, constantly correcting for the dramatic time dilation between their quiet pocket and the bustling universe beyond. Their reality would be one of profound patience and isolation, watching a cosmic dance from which they are forever separated by the unyielding gravity of their own home. Our own sense of a shared, universal present is a comforting illusion. The confirmation that entire galaxies exist within their own distinct temporal realities forces a profound shift in perspective. Time is not a river flowing at one speed for all observers, but a vast, shimmering fabric where each thread moves to its own rhythm. This cosmic reality echoes ancient philosophical insights long before telescopes provided the proof. Heraclitus spoke of a world in constant flux where you cannot step into the same river twice. 2.5 millennia later, Immanuel Kant argued that time is not an absolute entity existing independently, but a fundamental framework of the human mind, a lens through which we necessarily perceive reality. Modern cosmology has now given these abstract ideas a physical, measurable form. The ticking of a clock is not just a personal experience, but a local condition, shaped by the specific gravitational and energetic environment you inhabit. This blurs the line we have always drawn between the objective world of science and the subjective world of experience. If two beings, one in a bustling galactic cluster and one in a silent void, could compare notes, they would not agree on the duration of cosmic events or even on what constitutes the present moment. Their realities, their very nows, would be out of sync. So where does this leave our own consciousness, our feeling of a continuous self moving steadily from one moment to the next? Is our personal flow of time, our stream of awareness, also a local phenomenon? We are forced to ask if the universe possesses a single, true history, or if history itself is fractured into countless versions, each true within its own temporal pocket. This deeper contemplation of time as a personal, relative condition sets the stage for the final, human part of this story. How did we, confined to our small world, ever come to grasp such a magnificent and counterintuitive truth? Isaac Newton's universe ran like a perfect, unwavering clock. He believed time was absolute, flowing at the same constant rate for everyone, everywhere, an immutable backdrop against which the cosmic drama unfolded. This was a comforting and intuitive idea, one that stood for centuries. Then came Albert Einstein. With his theory of relativity, he revealed that time was not a rigid stage but a flexible dimension, interwoven with space into a single fabric called spacetime. This fabric could warp and stretch, meaning a clock's tick was not universal but deeply personal, dependent on its speed and the local strength of gravity. Einstein gave us the theory, but it was Edwin Hubble who gave it a cosmic canvas. His monumental discovery that distant galaxies are all rushing away from us revealed an expanding universe, a dynamic stage where spacetime itself was stretching. This was the crucial piece that transformed time dilation from a curious theoretical prediction into an inevitable feature of the cosmos. If space is expanding and space and time are one entity, then the flow of time must be part of that expansion. The journey to prove this was long and meticulous. It began with foundational experiments like the work of Michelson and Morley, which inadvertently paved the way for relativity by showing that light speed was constant, a key that unlocked Einstein's new vision of reality. Decades later, astronomers began the painstaking work of mapping the universe's large-scale structure, revealing the great cosmic web of galaxy clusters and the vast, empty voids between them. This map was the final clue. It showed that the universe was not a uniform soup, but a landscape of hills and valleys in spacetime. In the dense hills, gravity would slow time. In the expansive valleys of the voids, the stretching of space would allow time to flow faster. Our current understanding is the direct result of this cumulative effort. Each generation of scientists built upon the foundations of the last, from Newton's absolute time to Einstein's flexible spacetime to Hubble's expanding universe, and finally to our modern maps of the cosmic web. We are now the beneficiaries of that entire history. equipped with the knowledge and the tools to finally go looking for those quiet galaxies where the clocks tick to a different rhythm, not as a thought experiment, but as a measurable fact of our universe. These virtual universes begin with a simple recipe. Scientists program the supercomputer with the known laws of physics and a set of initial conditions that mimic the universe just after the Big Bang, a hot, dense, nearly uniform soup of particles. Then they set the simulation in motion, watching as billions of years of cosmic evolution unfold in a matter of weeks or even days. The key ingredients are dark matter, which provides the gravitational scaffolding for the cosmic web, and dark energy, which drives the accelerating expansion. As the simulation runs, gravity pulls the dark matter into filaments and halos, and galaxies form at the densest intersections. The result is a breathtakingly realistic digital cosmos, a sprawling map of clusters, filaments, and vast, empty voids. Within this simulation, every single particle has a known position and velocity. This complete knowledge allows researchers to do something impossible in the real world. They can place a virtual observer anywhere they like, from the heart of a massive galaxy cluster to the deepest, emptiest void. From that vantage point, the simulation can calculate exactly how the flow of time would be perceived. It tracks how the gravitational potential and the expansion rate at that specific location would warp the local clock relative to the simulation's master time. This process turns abstract theory into a concrete, visual prediction. We can literally watch as pockets of slower and faster time emerge across the cosmic landscape, painting the virtual universe in a hidden palette of temporal colors. These simulated timelines become a crucial guide for real-world observation. When a telescope like the James Webb points at a distant, quiet galaxy, astronomers can look up its properties in their simulations. They can find 1,000 similar virtual galaxies and see what the models predict their time flow signature should be. Does the real data match the simulation? Any discrepancy is not a failure but a clue. It might mean our understanding of dark energy is incomplete, or that gravity behaves differently on cosmic scales than we thought. This constant back and forth between digital prophecy and observational truth is how we refine our picture of reality. The supercomputer becomes a time machine, not for traveling to the past, but for understanding the very fabric of time itself. Deep within the constellation of Boötes lies a sphere of nothingness so vast it defies human comprehension. The Boötes void is a cosmic chasm, a region of space hundreds of millions of light-years wide that contains almost nothing. If you were to place our own Milky Way at its center, the nearest major galaxy would be so far away its light would be a faint, lonely speck. This is the empire of silence. And drifting within this immense emptiness are a handful of isolated galaxies, the sole inhabitants of this great expanse. Among them is a spiral galaxy known as MCG +01020015, a string of numbers that astronomers have nicknamed the Loneliest Galaxy. It is the ultimate hermit, a single island of stars in an ocean of darkness stretching for unimaginable distances in every direction. This galaxy does not have neighbors. It has an absence of them. Its profound isolation makes it one of the purest places in the universe to test our ideas about time. Here, far from the gravitational pull of any cluster, the stretching of space-time should be almost unimpeded. The local clock set by the void itself should be ticking at its own distinct rhythm. When astronomers point their spectrographs at the loneliest galaxy, they are not just measuring its distance. They are reading its personal timeline. The starlight we receive from it has traveled for hundreds of millions of years, and encoded within its specific frequencies is a record of how time was flowing there when those photons began their journey. The data reveals a galaxy that seems older and quieter than its counterparts in denser regions. Its star formation is minimal, as if the entire system has settled into a deep, prolonged slumber. The chemical signatures in its stars suggest a slower, more drawn-out evolution, precisely what we would expect if time itself were stretched within its gravitational well, set against the backdrop of an accelerating void. The properties of this galaxy are a perfect match for a place where a second is just a little bit longer, where the great cosmic cycles of birth and decay are unfolding with a noticeable lethargy. This is no longer just a theoretical prediction. It is a description of a real place, a specific set of celestial coordinates where the universe has chosen to run on a different schedule. Defining the present moment across the cosmos is a problem that challenges our most basic intuitions. Your now and the now of a distant, quiet galaxy are not the same instant. This is not just because light takes millions of years to travel the distance between us, but because the very flow of time in that galaxy is different from our own. When we look at its faint light, we are peering into its past. To understand its current state, we must perform a remarkable feat of cosmic calculation. We must account for the light travel time, yes, but we must also calculate how much its local time has been stretched or compressed by gravity and the expansion of its home void relative to our own timeline. Astronomers use a concept called the hypersurface of simultaneity to tackle this. Think of it as a cosmic snapshot, a single, universal moment frozen across all of space. But this is not a flat photograph. It is a warped and rippling surface, curved by the uneven distribution of matter and energy throughout the universe. A point on this surface near a massive galaxy cluster would be bent backward in time relative to a point in an empty void, because time flows more slowly in the cluster. Constructing this surface requires knowing the entire expansion history of the universe and the precise gravitational landscape in between. It means inputting data from the cosmic microwave background, the large-scale structure of galaxy clusters and voids, and the measured properties of dark energy into our most sophisticated models. Only then can we theoretically sync our clock with a clock in that distant galaxy and ask what it is doing at this very moment according to the cosmos. This is not a simple subtraction of travel time. It is a complex recalibration of reality itself. The sheer intellectual effort involved reveals a profound truth. To even ask a question as simple as what is happening there now requires the combined power of general relativity, cutting-edge cosmology, and supercomputing. We are not just looking at the past, we are learning to read the universe's complex and beautiful temporal map. Gravity's influence goes beyond merely bending a beam of light. It can also warp our perception of time itself, acting as a lens for the very moments we observe. This is the fourth mechanism, a subtle but profound idea known as the lensing of time. You are already familiar with gravitational lensing, where the mass of a foreground galaxy cluster acts like a giant magnifying glass in space, warping the fabric of spacetime so drastically that it distorts and multiplies the images of galaxies behind it. But if mass can bend the path of light which travels through spacetime, then it must also affect the time component of that fabric. A massive structure, a great cluster of galaxies lying directly between us and a distant, quiet galaxy, does more than just curve the light's trajectory. It creates an integrated gravitational potential along the entire path the light must travel. Every bit of that journey through warped space leaves a tiny imprint on the light's perception of time. The result is a secondary cumulative time dilation effect. The clock of the quiet galaxy we are observing does not just tick at its own local rate, set by its own gravity and its home void. Its signal is also filtered through the immense gravity well of the lensing cluster, which adds its own temporal signature, subtly slowing the apparent flow of time we measure from our vantage point. Think of it as listening to a recording that was made in a slow time zone and then playing it back on a machine that also runs a little slow. The combined effect is a compounded slowing, a temporal echo that is layered on top of the primary signal. While the effect is incredibly small and has not yet been directly observed, its potential is staggering. Future high-precision missions, equipped with exquisitely sensitive instruments, may one day detect this faint whisper. They would need to measure the light from a background galaxy with such accuracy that they could distinguish the tiny, additional redshift caused by the foreground cluster's temporal lens from all the other factors. Success would mean our maps of cosmic time would gain a new dimension of complexity. We would not only be plotting where time flows fast or slow, but also accounting for how the great gravitational structures of the universe bend and focus the river of time itself, creating a cosmic hall of mirrors for our most fundamental experience of reality. The cosmos is on a one-way journey toward absolute silence. As dark energy's relentless push accelerates the expansion of the universe, the distant future holds a profound transformation. Every galaxy we see today, from the bustling spirals to the quiet ellipticals, will eventually become an isolated island. The great clusters and filaments of the cosmic web will be stretched and torn apart, their gravitational bonds overcome by the thinning of space itself. In that far future epoch, the peculiar state of the quiet galaxies we study today will not be an anomaly. It will be the universal condition for all that remains. The phenomenon of localized time, of clocks ticking at different speeds in different places, will become the dominant rule of reality. As the voids between these isolated galactic remnants grow to encompass almost all of space, time within those emptinesses will run faster and faster, unhindered by the fading whisper of gravity. This vision is not mere speculation. It is the direct projection of our most successful model of the cosmos, the lambda-CDM model, which weaves together dark matter, dark energy, and the standard laws of physics. The model forecasts a cosmos growing ever colder, darker, and more silent. The frenetic energy of the early universe, the brilliant bursts of star formation, the majestic collisions of galaxies, all of it will subside into a deep, permanent calm. The universe will become a collection of lonely galaxies, each burning its final stars in a pocket of slowed time, separated from all others by an ever-widening gulf of void where time rushes forward into nothingness. It is a future of profound isolation and temporal disparity, a sobering yet awe-inspiring destiny written into the fabric of spacetime itself. The idea of visiting yesterday is a powerful fantasy, but the reality of cosmic time dilation offers a different kind of journey. Science fiction often portrays gravity's time warp as a gateway to the past, a starship plunging toward a black hole to emerge in a bygone era. This is a compelling story, but it misrepresents the actual physics at play in the quiet galaxies we have been exploring. The difference in the flow of time between a galactic void and a dense cluster is not a bridge across the centuries. It is a divergence in the very speed at which moments accumulate. Imagine two identical clocks, one placed in the heart of a quiet galaxy and another left here in our solar system. If we could see both at once, the clock in the galaxy would fall behind ours, second by second, over millions of years. It is not traveling to our past, it is simply ticking more slowly, forever lagging in a race it cannot win. The present moment in that distant galaxy is still its own present, moving forward along its own timeline, just at a more lethargic pace. This is a crucial distinction. We are observing a difference in rate, not a reversal of history. The phenomenon is governed by what physicists call gravitational time dilation, a one-way effect that always slows a clock in a stronger gravitational field relative to a weaker one. You can only ever fall behind, never go back. This stands in stark contrast to the far more speculative concept of closed time-like curves, a theoretical possibility only in the extreme mathematics describing rotating black holes or wormholes sustained by exotic matter. These are not features of the serene, isolated galaxies we are discussing. Their altered time is a gentle, persistent, and irrevocable slowing, a testament to the fact that the universe has many rhythms but only one direction. By clarifying this, we ground a wondrous cosmic truth in real science, preserving the genuine awe that comes from understanding how the universe truly works, not just how we might wish it to be. The difference between a bustling galactic cluster and a silent void is like the difference between a clock on a busy city street and one on a remote mountain peak. The city clock is surrounded by the constant gravitational noise of skyscrapers, subways, and millions of people, a dense environment that subtly weighs upon the fabric of space-time, slowing its tick. The mountain clock, high in the thin, clean air, experiences a far quieter gravitational field. Over eons, the mountain clock would pull ahead, second by accumulated second, running faster in its tranquil isolation. This is the core of the analogy, a way to shrink the cosmos down to a human scale. Another powerful image is that of sound. A dense galaxy cluster is like a crowded, noisy room where the din of conversations makes it impossible to hear a single, quiet voice. The subtle stretching of spacetime is lost in that cosmic cacophony. A quiet galaxy, by contrast, is like an anechoic chamber, a space of such profound silence that you can hear your own heartbeat. In that stillness, the faint whisper of time flowing at a different rate becomes audible. Think also of two rivers. One flows through a narrow, rocky canyon, its water churning against the banks and boulders, its progress slowed by the constant friction and obstacles. This is time flowing within a massive cluster. The other river emerges into a wide, flat plain, its waters spreading out and flowing smoothly, unimpeded toward the sea. This is time in the void, flowing swift and deep. We can even turn to biology. A fungus growing on a nutrient-rich, crowded log might sprout and decay in a rapid, frantic cycle. Yet a lichen on a high, wind-swept rock grows with an incredible slowness, adding mere millimeters over a century. Its biological clock is set to a different, more patient rhythm, just as the stellar life cycles in a quiet galaxy are stretched across far longer eons. These analogies are not perfect, for they translate a four-dimensional fabric into our three-dimensional experience, but they serve a vital purpose. They give our minds a foothold, a way to grasp a truth that otherwise slips through our fingers like starlight. They remind us that the universe's most profound secrets are not always locked in complex equations, but are often echoed in the simple, rhythmic patterns of our own world. If entire galaxies can live and die by clocks set to different tempos, what other cosmic rhythms are we only just beginning to sense? Our cosmic search for these silent, time-shifted islands is about to leap forward. New astronomical missions are being launched with the specific goal of mapping the dark, unseen architecture of the universe, and in doing so, they will find thousands of these quiet galaxies. The European Space Agency's Euclid Telescope and NASA's upcoming Nancy Grace Roman Space Telescope are not general-purpose observatories. They are specialized cosmic cartographers designed to create the most extensive and precise three-dimensional maps of the cosmos we have ever seen. Their power lies in their enormous fields of view. While the James Webb Space Telescope is a powerful magnifying glass, peering intensely at a single, distant object, these new telescopes are like wide-angle lenses capturing sweeping panoramas of the sky. They will survey huge volumes of space, peering deep into the cosmic voids that older surveys could only sample in small, scattered pieces. Their infrared eyes are crucial, allowing them to see through the cosmic dust that can obscure distant galaxies, revealing the true, faint population of the emptiest regions. How will they identify a quiet galaxy? The process is a statistical treasure hunt. These telescopes will measure the precise positions, shapes, and distances for millions upon millions of galaxies. From this vast census, astronomers will filter the data, looking for the specific signatures of isolation. They will find galaxies that are not just far from their neighbors, but truly alone, residing in the profound emptiness where the density of matter drops to nearly zero. They will look for the telltale red color of an aging stellar population, a sign that star formation has long since ceased and the galaxy has settled into its deep temporal slumber. The result will be a catalogue of not just a few curious examples, but thousands of candidate quiet galaxies. This large, clean sample is the key to everything. With so many examples, scientists can move from intriguing anecdotes to solid, statistical truth. They can measure the average properties of these galaxies, compare their redshifts with incredible precision, and see if the time dilation signal we have tentatively detected holds firm across the entire population. Any subtle anomaly in their light, any persistent shift in their atomic clocks, will become undeniable when seen repeated in thousands of different galaxies, scattered across billions of light years. This is the next frontier. It transforms the search from a fascinating possibility into a rigorous test of our most fundamental theories about gravity, dark energy, and the nature of time itself. We are on the verge of not just finding a few more quiet places, but of understanding the temporal geography of our entire universe. Every prediction about time is a test of Einstein's grand vision. When we observe a quiet galaxy and measure the subtle slowing of its clock, we are not merely collecting data. We are placing a stone on one side of a cosmic scale, with Einstein's theory of general relativity on the other. A perfect match confirms the incredible accuracy of a century-old idea, but a discrepancy, however small, would be a seismic event in physics. It would mean that our understanding of gravity, the force that sculpts the cosmos, is incomplete. This is the immense weight carried by the faint light from these silent islands. One compelling alternative is known as modified Newtonian dynamics, or MND. This theory was proposed to explain why galaxies seem to rotate too quickly to be held together by their visible matter alone, without invoking the mysterious presence of dark matter. MND suggests that gravity behaves differently at extremely low accelerations, like those found in the faint outskirts of galaxies or in the profound emptiness of a cosmic void. Its prediction for time dilation would therefore be distinct. In Einstein's universe, the slowing of time is tied directly to the total gravitational potential, a sum of all the mass present, including dark matter. In a MND-dominated cosmos, the effect would be governed by a modified law, one that could lead to a different amount of time warping in the same low-density environment. The precise way a clock ticks in a quiet galaxy becomes a direct arbiter between these two competing descriptions of reality. It asks a fundamental question. Is the cosmos filled with an invisible substance that grips galaxies with its gravity, or are the laws of gravity themselves different in the quiet places? This search extends even further, touching upon the dream of a unified theory of physics. General relativity describes the cosmos on its largest scales, while quantum mechanics governs the bizarre world of the atom. The two are famously incompatible. Any crack in the foundation of general relativity, revealed by an anomalous measurement of time, could be the opening that theorists need. It might point the way toward a deeper, more complete theory, one that seamlessly merges the very large with the very small. So when an astronomer studies the redshift of a lonely galaxy, they are doing more than astronomy. They are conducting a fundamental experiment on the nature of reality itself, an experiment where the universe is both the laboratory and the result. The most powerful telescopes reveal galaxies of breathtaking serenity. They are not the fiery pinwheels of our galactic neighborhood, but vast, smooth ellipses of burnished gold and deep crimson, suspended in a void of absolute black. There are no ragged spiral arms, no brilliant blue nurseries of newborn stars. Their forms are pristine and undisturbed, their light the accumulated glow of countless ancient suns that have burned for eons in perfect tranquility. To gaze upon one is to feel a hush fall over the cosmos, a sense of peace that transcends the violent chaos of most cosmic evolution. These islands are not just physically quiet, they are visually silent, their very appearance an echo of the deep stillness in which they reside. They seem to hold an ancient wisdom, a patient understanding of the universe that we, in our bustling galactic city, can scarcely comprehend. The beauty here is not one of explosive creation, but of graceful endurance. It is the beauty of a finished symphony, where every note has found its place and all that remains is the lingering, resonant chord. This aesthetic experience is not separate from the science, it is a direct consequence of it. The same physical laws that slow their clocks and stretch their timelines have also sculpted their majestic, placid forms. Their isolation allowed them to age without interruption, their gravity settling their stars into these calm, spherical distributions. When we analyze the spectrum of their light to measure time dilation, we are reading the same history that paints their stunning portrait. The pursuit of this knowledge, then, is not a cold, clinical exercise. It is a journey that marries the rigor of mathematics with the soul of poetry, reminding us that to understand the universe is also to fall in love with its infinite, quiet variations. What other forms of beauty are waiting in the darkness, hidden by distance and the limits of our own perception? A fifth possibility emerges from the very idea of nothingness itself. The vacuum metamorphosis model proposes that empty space is not merely a passive backdrop, but a substance capable of a fundamental transformation. Picture a block of ice melting into water. The substance is the same, but its fundamental properties, its very state of being, have changed. This model suggests that in the extremely low-density environments of cosmic voids, the vacuum of space undergoes a similar phase transition. The energy inherent in the vacuum itself shifts, changing the local rules of the game for spacetime. This is not the constant, gentle push of the cosmological constant. It is a dramatic, localized event that alters the fabric of reality in those quiet places. The consequence for time is profound. If the properties of spacetime itself are changed in a void, then the flow of time would not just be a little faster. It would be drastically different, warped in a way that far exceeds the predictions of our standard models. A clock placed in such a region would race ahead at a pace we would find difficult to comprehend, its seconds blurring into years compared to our own. While this idea remains speculative and is not the mainstream view, its value is immense. It reminds us that our current understanding of the cosmos is a map, not the territory itself. The existence of these quiet galaxies, with their subtle temporal mysteries, is the very reason such bold theories are proposed. They are the anomalies that keep science alive and questioning, forcing us to wonder if the universe still holds deeper, more astonishing layers of reality waiting to be uncovered in the silence. The hunt for these cosmic hermits is too vast for any single team of astronomers. Vast digital sky surveys have catalogued hundreds of millions of galaxies. a number so immense that professional scientists could never hope to examine each one. This is where the power of the crowd comes in, through projects like Galaxies Zoo. This citizen science platform invites anyone with an internet connection to become a cosmic explorer, helping to sift through this mountain of data and spot the telltale signs of a quiet galaxy. You are presented with a real, often never before seen image of a galaxy and asked simple but crucial questions. Is it smooth and round, or does it have spiral arms? Is it simply a star? Each classification from thousands of volunteers around the world adds a single data point to a massive collaborative effort. It is through this collective human lens that the rarest and most interesting objects, including those profoundly isolated galaxies, are flagged for further professional study. The process transforms abstract data into a personal discovery. One volunteer, a retired teacher named Hanny van Arkel, was simply browsing the Galaxy Zoo images when she noticed a strange, glowing green object near a distant spiral galaxy. It was unlike anything she had ever seen. Her curiosity sparked a full astronomical investigation, leading to the discovery of an entirely new class of object, now known as Hanny's Voorwerp. This was not a quiet galaxy, but it proved a profound point. A curious person with no formal training could make a genuine contribution to our understanding of the universe. Stories like this are not uncommon. Other volunteers have identified gravitational lenses, oddball star clusters, and thousands of the serene, red ellipticals that are prime candidates for our quiet galaxies. This inclusive approach shatters the idea that cosmology is the sole domain of a small elite. It demonstrates that the exploration of the cosmos is a collective human endeavor, a shared project that connects us all to the grand mysteries of space and time. The next time you look up at the night sky, remember that you too could be the one to spot a distant island of time, a silent galaxy whose secrets are waiting for a curious mind to find them. A single sky survey can capture the light of 100 million galaxies, a flood of day, so immense it would take a human 1,000 lifetimes just to look at each one. This is the new reality of cosmology, a field now defined by a deluge where finding a few thousand quiet galaxies is like searching for a handful of specific, silent pebbles on a beach that spans an entire continent. To solve this, astronomers have turned to a powerful ally, artificial intelligence. Specially trained machine learning algorithms are now the primary tool for sifting through this cosmic haystack to find those rare, temporally shifted needles. The process begins with training. Scientists feed a neural network thousands of example images and spectra of galaxies that are already well understood. They show it bustling spirals, dense ellipticals in clusters, and the serene, isolated galaxies we are hunting for. The algorithm learns to recognize the subtle patterns that define a quiet galaxy, its smooth, red shape, its specific light signature, and its statistical isolation from any neighbors. It learns to see what a human eye might miss, the faint photometric clues in the broad colors of starlight that hint at an ancient, quiescent stellar population. One of the most powerful techniques is the convolutional neural network, a system modeled loosely on the human visual cortex. This type of AI does not just see a galaxy as a single blob of light. It breaks the image down into layers of features, analyzing edges, textures, and complex shapes to build a profound understanding of its form. It can distinguish a truly isolated galaxy from one that simply appears alone from our perspective, but is actually part of a distant cluster. Once trained, this digital hunter can analyze millions of objects in a fraction of the time it would take a team of researchers, flagging the most promising candidates for deeper investigation with our most powerful telescopes. But the real magic happens with the spectra. The neural network is trained to read the story written in the rainbow of starlight, to detect the infinitesimal shift of the hydrogen alpha line and other atomic fingerprints against the background of cosmic expansion. It learns to separate the signal of true time dilation from the noise of interstellar dust, instrumental error, and other cosmic phenomena. This is not a simple search. It is an exercise in pattern recognition at a scale and precision that is fundamentally beyond human capability. The AI becomes a partner in discovery, scanning the digital universe not for what we already know, but for the subtle anomalies that point toward what we have yet to understand. It is on this rapidly advancing technological frontier that our search for silent galaxies is transforming from a targeted inquiry into a comprehensive census of cosmic time. A profound discovery always carries a certain weight of responsibility. When we learn that time itself is not a universal constant but a local condition, we are not just adding a new fact to a textbook. We are subtly altering the foundations of human understanding, and with that shift comes a need for careful thought. The revelation that entire galaxies exist in their own distinct temporal realities, that the cosmos ticks to the rhythm of countless different clocks, challenges narratives that have anchored human cultures for millennia. Many of our oldest stories, from religious texts to ancient myths, are built upon a stable, absolute stage of space and time, a fixed backdrop for the drama of existence. To introduce a universe where this stage is flexible and fractured can feel, to some, like pulling the ground out from under our feet. It forces a re-examination of concepts like eternity and the present moment, ideas that are central to how we find meaning. The ethical question is not whether this knowledge should be pursued, for the drive to understand our universe is a fundamental part of our humanity. The responsibility lies in how we share it. We must present these cosmic truths not as a cold dismissal of older worldviews, but as a grander, more majestic vision that can coexist with a sense of wonder and purpose. This is not about replacing one dogma with another. It is about expanding the conversation, inviting everyone to see that our place in the cosmos is not diminished by its complexity, but made more precious. Our tiny world, with its single, shared second, becomes the unique vantage point from which we can perceive the magnificent, swirling diversity of time itself. How do we ensure that this new perspective fosters unity and awe, rather than confusion or a sense of cosmic insignificance? The answer lies in humility. The scientist who measures the redshift of a lonely galaxy and the philosopher who contemplates the nature of a moment are engaged in the same essential project, trying to read the story of reality. By weaving our scientific discoveries into the broader tapestry of human experience with care and respect, we do not just learn about the universe, we learn about ourselves, and we build a bridge between the objective cosmos and the subjective heart, ensuring that our growing knowledge brings wisdom, not alienation. Our cosmic vision extends only to the edge of a great horizon. This is the limit of the observable universe, a sphere centered on us with a radius of about 46 billion light-years. We cannot see anything beyond it, not because our telescopes are too weak, but because the light from those more distant regions has not had enough time to reach us since the beginning of everything. The universe is simply not old enough for that information to have arrived. This cosmic horizon places a permanent veil over the vast majority of existence, and it forces us to confront a humbling question about our quiet galaxies. We have begun to map the subtle differences in time flow within our observable bubble, but does this temporal tapestry continue in the same intricate patterns beyond the veil, in realms we can never access? Or could the nature of time itself be fundamentally different in those unseen depths? The quiet galaxies we study are the farthest, faintest beacons we will ever see, each one a data point at the very edge of our knowledge. Their stretched timelines and ancient starlight represent the final page of a story we can read. What lies beyond that final page is pure conjecture. Some theoretical models suggest the universe might be infinite, a never-ending expanse of galactic clusters and immense voids stretching forever, with the patterns of time repeating in an endless fractal. Other, more exotic ideas propose that the laws of physics could vary in those unobservable regions, that gravity or the strength of dark energy might be different, creating pockets of time that flow at rates we cannot even conceive. This horizon is not a physical wall. It is a frontier of information, a fundamental limit imposed by the speed of light and the age of the cosmos. It means our entire understanding of the universe, from the quietest galaxy to the fastest ticking clock, is built upon a finite sample. We are like sailors on a vast, foggy ocean, able to chart only the islands within a certain distance. We can infer the existence of a greater continent from the patterns we see in the water and the stars, but we can never sail there to confirm its shape. This inherent limitation transforms our search for quiet galaxies from a simple census into a profound philosophical exercise. Every measurement we make, every redshift we analyze, is an attempt to understand the whole of reality by studying a single, isolated room. The ultimate nature of the cosmos, the complete story of time, may forever remain a beautiful, tantalizing mystery, hidden just beyond the reach of our most powerful instruments and our most brilliant minds. The universe reveals itself not as a single story, but as a grand symphony, with each region playing its own distinct tempo. We have gathered the threads of evidence, from the subtle warping of starlight to the faint echo in the cosmic microwave background, and they weave together into a single, coherent picture. Gravity acts as the great brake, slowing time in crowded galactic cities. Dark energy is the relentless accelerator, stretching the emptiness of voids and letting time run swift and free. The quiet galaxies are the precise locations where these two fundamental forces meet in a delicate balance, their isolation making the resulting time dilation something we can actually measure. This interplay creates a vast, invisible map of temporal zones across the cosmos. Picture a topographical chart of the universe, but instead of showing elevation, it charts the speed of time itself. The bright, dense knots of galaxy clusters are deep valleys of slow time where clocks tick with a noticeable drag. The vast, empty voids are the high plateaus where time rushes forward like a mountain river. Our quiet galaxies are not random outliers. They are the expected inhabitants of these temporal highlands. Their serene existence and ancient stars are a direct consequence of living in a place where the local clock has been set by the void for billions of years. This synthesis transforms a collection of fascinating facts into a fundamental law of cosmic geography. The flow of time is not a mystery. It is a variable, a physical property of a region, as real as its temperature or its density. Every piece of evidence, from the redshift anomalies to the altered life cycles of stars, points to this same profound conclusion: the universe is not just a place. It is a multitude of times, all unfolding at once, a breathtaking tapestry of nows that are forever out of sync. What does this unified vision tell us about our own fleeting moment within this grand temporal architecture? We have journeyed to the silent corners of the cosmos, where time itself marches to a different drummer. From the fundamental principles of relativity to the cutting-edge data from our most powerful telescopes, the evidence is compelling. Our universe is not a monolithic entity governed by a single, universal clock. It is a vast and intricate tapestry of countless temporal flows, a symphony of nows playing in different keys and tempos. The quiet galaxies we have explored are far more than distant curiosities. They are living proof of this cosmic principle, natural laboratories where the subtle interplay of gravity and dark energy writes the local rules for existence. They are windows into the deepest, most fundamental workings of spacetime itself, offering us a glimpse of a reality far more fluid and magnificent than our everyday experience suggests. Let this entire exploration stand as a powerful reminder of the universe's boundless capacity for wonder, its endless ability to surprise and humble us with its complexity. The next time you find yourself under a clear night sky, we encourage you to look up with new eyes, see not just points of light but entire islands of time. Share these ideas, these stories of silent giants and rushing voids with someone else, and never, ever stop questioning the beautiful, mysterious nature of reality itself.